Welcome to a journey through the infinite cosmos, where we unravel mysteries of the universe, exclusively here on Dark Sky Dive. Today we are going to deconstruct the massive, mind-bending distance that separates our blue home planet from the giant Jupiter. We all remember those colorful diagrams in our science textbooks that showed the planets lined up neatly next to each other. However, those simple drawings were a necessary lie, created just so everything could fit onto a single piece of paper. In reality, the space between these celestial bodies is a vast, empty void that the human brain struggles to comprehend. The average distance to Jupiter is about 484 million miles, a number that defies our daily logic. That is nearly 780 million kilometers of freezing vacuum, radiation, and absolute silence separating us from the giant.
To understand this scale, imagine you get into your car and start driving at highway speeds towards the gas giant. If you maintained a constant speed without stopping for gas or rest, the journey would take longer than recorded history. If you left Earth 5,000 years ago, right when humanity invented the wheel, you would still be driving today. In fact, after 5 millennia of non-stop driving, you would not have even completed half of the journey to Jupiter. Let us try something faster, like a commercial jetliner, cruising at 550 miles per hour through space. Even at this impressive speed, the journey to the King of Planets would take approximately 100 years to complete. You would literally pass away from old age long before the massive striped clouds of Jupiter ever came into view. Even light itself, the fastest thing in the known universe, does not travel instantaneously across such a massive cosmic divide. It takes sunlight about 43 minutes to travel from the Sun to Jupiter, creating a significant delay in communication. This means that any signal sent from a probe at Jupiter takes nearly an hour to reach our screens here. Humanity first conquered this distance in 1972 with the launch of the legendary Pioneer 10 space probe mission. It was a groundbreaking mission designed to be the first object made by humans to ever traverse the asteroid belt. It took Pioneer 10 just under 2 years, specifically 21 months, to finally reach the Jovian system and fly by. This 2-year journey was considered a sprint at the time, proving that we could actually reach the outer solar system. However, later missions like the Galileo probe in 1989 faced a much more complicated and lengthy path to Jupiter. Due to the Space Shuttle Challenger disaster, new safety protocols prevented Galileo from using a powerful liquid-fueled upper-stage rocket. Engineers had to design a clever trajectory called VEEGA, using gravity assists from Venus and Earth to build up speed. This detour meant that Galileo had to fly inwards towards the Sun before it could finally head out to Jupiter. It swung by Earth twice, stealing momentum from our planet to fling itself fast enough to reach the outer giants. Because of this winding path, the journey took a staggering 6 years, testing the patience of scientists around the world. In 2006, humanity launched New Horizons, the fastest spacecraft ever to leave Earth's orbit at that time. It left Earth traveling at 36,000 miles per hour, a speed so great it crossed the Moon's orbit in hours. New Horizons reached Jupiter in just 13 months, a record-breaking time that showcased the raw power of modern rocketry. However, it did not stop. It used Jupiter merely as a gravity booster to speed up its journey towards Pluto. Looking to the future, the Europa Clipper mission aims to return to the Jovian system to study its icy moon. Even with modern technology, Clipper will take about 5.5 years to arrive, using gravity assist from Mars. The real game changer lies in nuclear thermal propulsion, a technology that could revolutionize how we travel deep space distances. With nuclear engines, we could potentially cut the travel time to Jupiter down to just 2 years, or even less. As we look back at Earth from this distance, we realize how small we are and how vast the cosmos is. Jupiter stands as a guardian of the outer solar system, a massive destination that challenges our engineering and our patience. The scale of this planet is immense, but the emptiness we must cross to reach it is even more staggering. For a human crew to make this journey, they would need to survive years of isolation in a tin can. Life support systems would need to be perfect, recycling every drop of water and breath of air for years. Radiation in deep space is a silent killer, requiring heavy shielding that adds mass and complexity to any manned vessel. But the reward is a miniature solar system of its own, with moons that may harbor oceans and potential alien life. Europa, with its subsurface ocean, is one of the most promising places to look for life beyond our Earth. Then there is Io, the most volcanically active body in the solar system, a hellscape of fire and brimstone. The Juno mission is currently there, braving the intense radiation belts to map the planet's magnetic and gravitational fields. Every bit of data Juno sends helps us understand not just Jupiter, but how our entire solar system formed. Jupiter was likely the first planet to form, gobbling up most of the material left over after the Sun was born. Its massive gravity shaped the destiny of the other planets, acting as a cosmic shepherd for the asteroid belt. Some scientists believe Jupiter acts as a shield, absorbing impacts that might otherwise cause extinction events on our planet. We witnessed this power in 1994, when comet Shoemaker-Levy 9 slammed into Jupiter with the force of nuclear bombs. Those scars were larger than Earth itself, a terrifying reminder of the violence that exists in our cosmic neighborhood. But let's return to the journey itself, specifically the challenge of crossing the gap between Mars and the gas giant. Contrary to sci-fi movies, the asteroid belt is not a crowded obstacle course. The rocks are separated by millions of miles. You could fly 1 billion spacecraft through the asteroid belt at once, and the chance of a collision is almost zero. The real danger is the cold. As you travel further out, the sun becomes just a bright star in the distance. Solar panels become less effective, which is why deep space missions often rely on nuclear batteries called RTGs for power. These generators use the heat from decaying plutonium to keep the spacecraft alive in the freezing darkness of the outer void. The Voyager missions also made this trek in the late 70s, paving the way for our understanding of the outer planets. They utilized a rare planetary alignment that occurs once every 176 years to tour the giants. This alignment allowed Voyager to visit all 4 gas giants, turning a 40-year trip into a 10-year grand tour. Beneath Jupiter's clouds lies an ocean of liquid metallic hydrogen, a substance that exists nowhere else in our daily lives. The pressure down there is so immense that it would crush a submarine as if it were made of aluminum foil. Deep in the center, there may be a rocky core, or perhaps the core is dissolved into the metallic ocean. Jupiter's magnetic field is the largest structure in the solar system. If visible, it would appear larger than the full moon. This magnetic monster emits powerful radio waves that sound like an eerie chorus of screams when converted into audio frequencies. In 1995, Galileo dropped a probe directly into the atmosphere to taste the chemistry of the clouds before dying. It survived for nearly an hour, sending back invaluable data about wind speeds, temperature, and the composition of the atmosphere. Eventually, the heat and pressure became too much, and the probe was vaporized, becoming one with the giant planet forever. So how do we conquer this distance faster? The answer lies in moving beyond chemical rockets and embracing new physics. Ion propulsion offers high efficiency but low thrust, great for cargo, but too slow for getting humans there quickly. Fusion drives, if we can master them, would allow us to travel at a small percentage of the speed of light. With fusion, a trip to Jupiter could become as routine as a steamship voyage across the Atlantic Ocean was historically. Imagine a future where scientists live on orbital stations above the Great Red Spot, studying the storms in real time. The moons of Jupiter could become refueling stops, providing water and fuel for ships venturing even further into the dark. Jupiter is just the gateway. Beyond it lies Saturn, Uranus, Neptune, and the Kuiper Belt, waiting for our arrival. But the technology is only half the battle. The human mind is not evolved to handle such profound isolation. At Jupiter's distance, Earth is so close to the Sun that it might be impossible to see with the naked eye. Real-time conversation is impossible. You say hello and have to wait nearly an hour to hear hello back from home. This is why artificial intelligence will be a crucial crew member, making split-second decisions when Earth is too far away. The ship must be autonomous, capable of repairing itself and navigating hazards without waiting for instructions from mission control. It all started 400 years ago when Galileo Galilei first pointed his spyglass at the sky and saw 4 stars. He realized those stars were moving around Jupiter, a discovery that shattered the idea that Earth was the center of everything. We have come a long way from a small glass lens to sending robots billions of kilometers into the abyss.
Telescopes like Hubble have revealed auroras on Jupiter that are hundreds of times more energetic than those on our planet. Now the James Webb Space Telescope looks at the giant in infrared, revealing details in the atmosphere we never saw before. These different views help us understand the complex weather systems that have been churning for centuries without ever stopping. We have observed the Great Red Spot shrinking, a mystery that scientists are still trying to solve with continuous monitoring. The atmosphere is a layer cake of clouds made of ammonia and water, creating complex chemistry driven by internal heat. Lightning strikes pierce the gloom, powered by water clouds deep within, exploding with energy that rivals nuclear bombs. On gas giants like Jupiter and Saturn, extreme pressure might even squeeze carbon into diamonds that rain down towards the core. To even begin the journey to Jupiter, we must first break the chains of Earth's gravity, requiring immense speed. Then we must climb out of the Sun's gravity well, fighting the pull of our star every mile of the way. The most fuel-efficient path is the Hohmann transfer, an ellipse that touches both Earth's and Jupiter's orbits perfectly. However, this efficient path requires patience, as launch windows only open every 13 months when the planets align. If you miss the launch window, you are stuck on Earth for over a year waiting for the geometry to repeat.
The European Space Agency has also joined the race with the JUICE mission, heading to explore the icy moons. JUICE faces a long 8-year cruise, taking the scenic route to save fuel for its orbital insertion at Ganymede. Its primary target is Ganymede, the only moon known to generate its own magnetic field, a unique puzzle piece. Ganymede is a monster moon, actually larger in size than the planet Mercury, making it a planetary world in its own right. Scientists suspect it hides a deep ocean beneath its crust, containing more water than all of Earth's oceans combined. Then there is Callisto, an ancient battered world that holds the record for the most heavily cratered object we know. Callisto orbits far from Jupiter's radiation belts, making it the safest location for a potential future human outpost. Jupiter's gravity is 2.5 times stronger than Earth's. A 100-pound person would weigh 250 there. But you could never stand there. There is no solid surface, just an endless descent into crushing darkness and heat. Deep inside, the temperature soars to 24,000 degrees Celsius, hotter than the surface of the sun itself. Some call Jupiter a failed star, but it would need to be 75 times more massive to ignite nuclear fusion. However, it still radiates more heat into space than it receives from the sun, generating energy from gravitational contraction. For a trip to Jupiter, prepackaged food won't be enough. We need to master growing crops in deep space. Zero gravity wreaks havoc on the human body, causing muscle atrophy and bone loss during the long transit times. Future ships will likely need rotating sections to create artificial gravity, keeping the crew healthy for the arrival. Hibernation technology, often seen in movies, is being researched to let crews sleep through the boring years of travel. Scientists are studying how bears hibernate to see if we can induce a similar metabolic state in human astronauts. If we can sleep for the journey, we save massive amounts of food and air, making the ship lighter and faster. The Ulysses mission used Jupiter's gravity not to speed up, but to fling itself out of the planetary plane completely. It needed Jupiter's massive pull to bend its path so it could study the unexplored north and south poles of the sun. Cassini, famous for exploring Saturn, also made a pit stop at Jupiter in the year 2000, capturing stunning imagery. For a brief time, we had 2 robot ambassadors at Jupiter, working in tandem to study the giant's magnetic environment. We often forget that Jupiter has rings too, though they are made of dark dust and are very hard to see. These rings are created by dust kicked up from meteor impacts on the small inner moons, constantly replenished over time. Jupiter also herds 2 massive groups of asteroids called Trojans, trapped in stable gravity pockets ahead and behind it. NASA's Lucy mission is currently on its way to visit these time capsules, which have remained untouched for billions of years. These asteroids are the fossils of planet formation, trapped by Jupiter's gravity, waiting for us to tell their story. The gap between our best engines and the speed of light is humiliating. We are crawling while the universe sprints. At our current speeds, relativistic time dilation is negligible, but it becomes a factor if we ever achieve near-light propulsion. Projects like Breakthrough Starshot propose using giant lasers to push tiny light sails to incredible speeds, reaching Jupiter in days. However, this technology can only carry gram-sized probes, not heavy scientific equipment or human explorers. Antimatter propulsion is the holy grail,
offering the highest energy density, but it remains incredibly difficult and expensive to produce. Currently, producing just a single gram of antimatter would cost trillions of dollars and take millions of years. For now, we are stuck with chemical fire, burning dinosaur juice and oxygen to push ourselves off this rock. SpaceX's Starship promises orbital refueling, which could allow us to send massive payloads to Jupiter without needing tiny probes. A fully fueled Starship could theoretically land on Callisto, delivering tons of equipment to build a permanent base. Landing on these moons is hard because there is no atmosphere to slow you down. You must use fuel to brake. Gravity assists are free energy, but they require absolute mathematical precision. A tiny error leads to missing the target by millions. We send these robots out to die alone in the dark, transmitting their final discoveries until their batteries fade away. When the Cassini mission ended, scientists wept, mourning the robot as if it were a dear friend passing away. Future concepts include a cryobot that melts through the ice of Europa to deploy a submarine into the alien ocean. If we find life there, huddled around thermal vents, it would fundamentally change our understanding of biology in the universe. The ice shell is kilometers thick, harder than concrete at those temperatures, posing a massive drilling challenge for engineers. Sending data back through miles of ice requires a chain of relay stations, adding more points of failure to the mission. We rely on the Deep Space Network, a trio of massive antenna arrays around the globe, to hear these whispers. NASA is upgrading these ears to use lasers, allowing us to stream high-definition video from Jupiter in the future. The distance varies. At opposition, when Earth and Jupiter are on the same side, the gap shrinks significantly. But when they are on opposite sides of the Sun, the distance balloons, and the Sun blocks our communications completely. For about 2 weeks every year, we lose all contact with our probes as the Sun passes between us and them. During this silence, the spacecraft must take care of itself, executing pre-uploaded commands until the line clears again. Despite its size, Jupiter is the fastest spinning planet, completing a day in less than 10 hours. This rapid spin causes the planet to bulge at the equator, making it look squashed rather than a perfect sphere. The spin drives ferocious winds that tear the clouds into the iconic colored bands we see through our telescopes. The colors come from complex sulfur and phosphorus compounds, reacting with ultraviolet sunlight in the upper atmosphere. Jupiter is possessive of its secrets. The thick clouds prevent us from seeing what is happening deep down in the dark. Juno uses microwave instruments to peer below the cloud tops, revealing storms that have roots hundreds of miles deep. Unlike Saturn's neat hexagon, Jupiter's poles are a chaotic cluster of cyclones arranged in strange geometric crystal patterns. These storms rub against each other like gears in a machine, yet they remain stable and do not merge together. At this distance, sunlight is 25 times weaker than at Earth, making solar power a difficult engineering challenge. Juno had to be built with 3 massive solar wings, the size of a basketball court, just to generate enough power. Navigation at this range requires hitting a target the size of a city from a distance of 500 million miles. Future ships might use pulsars, the lighthouses of the universe, to navigate autonomously without relying on Earth. There is a type of cosmic horror in the sheer scale of Jupiter, a giant that could swallow our world whole. It is a place of deadly beauty, a masterpiece of fluid dynamics painted on a canvas of death and radiation. From the god of thunder in ancient mythology to the destination in sci-fi classics, Jupiter has always captivated us. Visionaries like Arthur C. Clarke imagined us traveling there long before we had the technology to actually do it. Reality has moved slower than fiction. We do not have giant crewed ships yet, but our robotic scouts are real. These missions cost billions of dollars, but the knowledge they return is priceless, expanding the horizons of human thought. The technology developed to survive the journey often finds its way back into our daily lives, improving life on Earth. Exploring the outer solar system is too big for one nation. It requires the cooperation of the entire human species. China is also planning its own missions to Jupiter, marking the beginning of a new era of international deep space exploration. Will this be a new space race, or a collaborative effort to unlock the secrets of the Jovian system together? Planetary science is a multi-generational endeavor. Those who launch the mission often retire before the spacecraft reaches its destination. The data collected today will be studied by students who haven't even been born yet, a legacy for the future. Jupiter's Europa is not alone. Ocean worlds seem to be common, suggesting the universe might be teeming with hidden life. We must be careful not to contaminate these worlds with our own bacteria, preserving their pristine environments for study. This is why Galileo was intentionally crashed into Jupiter, to ensure it would never accidentally crash into and contaminate Europa. Juno will eventually meet the same fiery fate, a noble sacrifice to protect the potential life on the icy moons. In the distant future, we might harvest helium-3 from Jupiter's atmosphere to power fusion reactors across the solar system. The giant planet could become the gas station of the solar system, the final stop before heading to other stars. As Carl Sagan famously said, somewhere, something incredible is waiting to be known, perhaps hidden in Jupiter's clouds. Before we go there in person, virtual reality using real mission data will allow us to experience the view from home. Inspiring the next generation of engineers and dreamers is the most immediate benefit of these grand voyages into the void. Remember, Jupiter is 5 astronomical units away, 5 times the distance from the Earth to the Sun. At 5 astronomical units, the Sun is just a piercingly bright point light source, casting sharp, harsh shadows in the vacuum. The average temperature hovers around -145 degrees Celsius, a cold that freezes atmosphere into ice. It is the gateway to the outer dark, the last brightly lit outpost before the dim realms of Uranus and Neptune. Jupiter acts as the gatekeeper, its gravity defining the boundary between the inner rocky planets and the outer gas giants. Its gravity was so disruptive that it prevented a planet from forming in the asteroid belt, leaving only debris behind. We might owe our very existence to this giant, which cleared the solar system of debris that could have destroyed Earth. Though some recent theories suggest it might have also flung rocks at us, playing a chaotic role in our history. The dance of gravity is complex. Jupiter is the dominant partner, pushing and pulling everything else to its rhythm. Europa Clipper carries ice-penetrating radar that will see through the crust, mapping the depth of the hidden ocean. It will look for pockets of liquid water within the ice shell, which could be accessible habitats for life. The probe will attempt to fly directly through water plumes erupting into space, tasting the ocean without needing to land. This allows us to analyze the chemical composition of the alien ocean, looking for the building blocks of organic life. To survive the radiation, Clipper's electronics are housed in a thick titanium vault, a bank vault for computer chips. It won't orbit Europa directly. Instead, it will perform elliptical flybys to minimize time spent in the radiation danger zone. Each flyby is a precious opportunity, gathering gigabytes of data before retreating to the safety of deep space. These missions are a testament to human perseverance, the result of thousands of careers dedicated to exploration. We are the modern equivalent of ancient sailors crossing the vast oceans, guided only by the stars and our curiosity. But this ocean is infinite, and the islands we seek are moving targets millions of miles away. The silence of space is profound. There is no sound, no wind, just the hum of the spacecraft's electronics. In that silence, there is a haunting beauty, a reminder that we are a small part of a majestic whole. The ultimate question drives us. Are we alone, or is the universe full of life waiting to be found? Jupiter and its moons offer the best chance in our solar system to answer that fundamental question once and for all. Even finding simple bacteria would prove that life is not a miracle unique to Earth, but a cosmic norm. That discovery would change philosophy, religion, and our understanding of our place in the cosmos forever. Advanced concepts like the Vesimer plasma engine could bridge the gap, offering a balance between speed and fuel efficiency. Powered by onboard nuclear reactors, these engines could sustain thrust for weeks, constantly accelerating the ship to higher speeds. Constant acceleration would not only get us there faster, but could also provide artificial gravity for the crew. But remember, you have to slow down. Half the trip is accelerating, and the other half is braking to stop. If you don't start braking halfway there, you will zoom past Jupiter and be lost in the interstellar void forever. We can use aerobraking, skimming the atmosphere to slow down, but at Jupiter speeds, the heat would be incredible. The heat shield would need to withstand temperatures that would melt almost any known material instantly. Bold concepts suggest scooping up the atmosphere during the pass to refill propellant tanks for the return journey. Getting there is hard, but getting back is even harder. you have to fight Jupiter's massive gravity to leave. A round-trip mission with current or near-future tech would consume a decade of an astronaut's life. They would return to a world that has moved on, missing 10 years of history, family growth, and life on Earth. Is it worth it? To touch the face of another world and expand the boundaries of human knowledge? Absolutely.
Jupiter is a natural laboratory for high-pressure physics, meteorology, and magnetic fields that we cannot replicate on Earth. By understanding the extreme weather there, we improve our models for weather and climate here on our own planet. If humanity is to survive in the long run, we must become a multiplanetary species, mastering deep space travel. Mastering the trip to Jupiter is the prerequisite for the ultimate challenge, traveling to other star systems. Our solar system is just our backyard. The real journey lies in the galaxy beyond, but we must learn to walk first. The child looking through a telescope tonight might be the commander of the first crewed mission to the Jovian system. We must continue to tell these stories, to inspire the curiosity and drive needed to solve the engineering challenges ahead. We have seen that the distance is vast, the environment is hostile, and the time required is immense. Yet, despite these odds, we have successfully sent our robotic avatars to explore, photograph, and taste this alien world. Technology is accelerating. What took Galileo 6 years might take future explorers only a fraction of that time. We are living in a golden age of planetary exploration, with more missions heading to the outer planets than ever before. We must never lose respect for the void. It is a harsh mistress that demands perfection from our machines and minds. Space is hard, and it punishes ignorance or carelessness with failure. But each failure teaches us how to succeed. Perhaps the journey itself is as important as the destination, pushing us to evolve and grow as a species. Jupiter spins on, indifferent to our struggles, a giant beacon calling us across the dark ocean of space. We will go back, not just with robots, but with human eyes to witness the great red spot in person. Imagine standing on the ice of Europa, watching the massive crescent of Jupiter rise over the horizon. What a view! It is in our DNA to explore, to cross the horizon, to go where it is dangerous and unknown. 484 million miles is not a barrier. It is merely a distance waiting to be bridged. Thank you for taking this long journey with us today, visualizing the true scale of our cosmic neighborhood. If you enjoyed this deep dive into the void, please hit the like button and subscribe for more cosmic content. Let us know in the comments, would you volunteer for a 10-year round trip to see Jupiter with your own eyes? Check out our other videos exploring the mysteries of Saturn, black holes, and the edges of the known universe. Until next time, keep looking up at the stars and wondering what lies in the dark sky above us. This has been a production of Dark Sky Dive. Safe travels through the void, and we will see you soon.